Class 11th, chapter number 7, Permutations and Combinations. So we'll learn the definition of permutation. A permutation is an arrangement in a definite order of a number of objects taken some or all at a time. Theorem 1. The number of permutations of n different objects taken r at a time, where 0 is less than r is less than or equal to n, and the objects do not repeat, is n into n minus 1, n minus 2, so on till n minus r plus 1, which is denoted by npr. So let us understand this more. Let r distinct places be filled up by n distinct objects when repetition is not allowed, and let the places be, say, x1, x2, x3, so on till xr. So since there are n distinct objects, x1 can be filled up in n ways, x2 can be filled up in n minus 1 ways, because here repetition is not allowed. So one object has been used in x1, so number of objects which can be filled up in x2 are n minus 1. Similarly, when we are filling this x3, when we are filling this x3, two objects are already filled up in one object in x1, one in x2. So in x3, how many objects we can fill up? N minus 2 objects. So same way, if you follow in xr place, how many objects we can fill up? N minus r minus 1. How we got this? If you see it carefully, in x1 we have n objects, in x2 one number less than 2, that is n minus 1. Here x3, so in x3 how many objects can be filled up? One number from n, we are subtracting one number less than 3, that is 2, so n minus 2. Same we follow in n, we'll remove r with one number less, that is n minus r minus 1, so that will become here n minus in bracket r minus 1. So we know that if if a work is there in which can be done in m ways, and there are sub parts in that. One part can be done in m ways, another part can be done in n ways, and so on. Then the total number of ways in which the work can be done is multiplying all those possibilities. So here we are having, by fundamental principle of counting, the number of ways in which we can fill up the r distinct places by n distinct numbers or n distinct objects when repetition is not allowed. That will be n into n minus 1, n minus 2, n minus 3, so on till n minus r plus 1. And we can rewrite this for, so this is the formula for npr, that is arrangement of n distinct objects in r places when repetition is not allowed. What is that? N into n minus 1, n minus 2, so on till n minus r plus 1. And this we can rewrite with the help of the notation, with the concept of factorial. We already know what is factorial. N factorial stands for the product of all the natural numbers starting from n till 1. Now here npr is equal to, we have got as n to n minus 1, n minus 2, n minus 3, so on till n minus r plus 1. So to get to use the form of factorial, what we'll do is we'll take this multiplication till 1. So here the last number which we are having is n minus r plus 1. So the next number will be n minus r, and then the next will be n minus r minus 1, so on till 1. So we'll multiply and divide by n minus r minus 1, so on till 3 into 2 into 1, numerator and denominator both. Now we can see that here npr, if you see the numerator of that this formula, we are getting the product of all the natural numbers starting from n till 1, so that can be written as n factorial. And you see the denominator, it is the product of all natural numbers starting from n minus r and ending at 1, so that is n minus r whole factorial. Therefore, what is npr? That is the arrangement of n distinct objects at r distinct place when repeat is not allowed, that is n factorial over n minus r whole factorial. So now let us go in some another concept, that is the number of permutation of n distinct objects taken r at time when repetition is allowed is n raised to r. Suppose there are, say, r distinct places, say x1, x2, x3, so on till xr, and they are to be filled up by n distinct objects, but repetition allowed. So in this case, what will happen? X1 can be filled up in how many ways? N ways. X2 can be filled up in n ways. X3 can be filled up in n ways, and so on. XR can be filled up in how many ways? N ways. So by fundamental principle of counting, the number of ways in which the permutation can be carried out will be equal to n into n into n into so on. So here permutation will be equal to permutation of n distinct objects at r distinct places when repetition is allowed is equal to n times, here n will come r times, so we will be getting equal to n raised to r. Now theorem number 3, the number of permutation of n objects where p objects are the same kind and rest all are different. So the formula for this n factorial over p factorial. Similarly, we can generalize this also. The number of permutation of n objects where p1 objects are of one kind, p2 are the same kind, so on till pk are of the kth kind, and the rest, if any, are different kind. Then the formula for that is n factorial over p1 factorial, p2 factorial, p3 factorial, so on till pk factorial. Now we'll see the logic behind 0 factorial equal to 1. For that we'll have to move back, and here we are having the formula of NPR. NPR stands for arrangement of n distinct objects at r distinct places when repetition is not allowed. So suppose in place of r, suppose we have n distinct objects. Suppose n distinct, let us say NPN. NPN stands for arrangement of n distinct objects at n distinct places. So in this case, if we apply this formula, it will be equal to n factorial over n minus, this will be here n and factorial. So we will be getting n factorial over 0 factorial. Now let us go in this here our initial step. Suppose now the places are, since there are n places and they are to be filled by n objects, so x1 can be filled up in n ways, x2 in n minus 1 ways, x3 in n minus 2 ways, and similarly this because this in place of xr it will be x, and that will be filled up in how many ways? In 1 ways, because all objects will be utilized. And so that means when we have to arrange n distinct objects at n distinct places and it is not allowed, that is equal to n factorial. And if we compare this, what will be getting? We will be getting here, therefore n factorial over 0 factorial will be equal to n factorial, and this can be written as 1. So comparing them, if we compare them, what we will be getting? We will obtain, this will give us 0 factorial equal to 1. So this is the logic behind taking 0 factorial as 1. So with this, our concept of permutations is complete.